Some physicists would say that the quantum mechanics questions come first. The questions about space and time come later. So when you're thinking about the interpretations of quantum mechanics, there are three main camps, you could say. The first camp is David Bohm and is referred to as the hidden variables theory. And so anyways, with that, I'm going to keep reading now from part 1 of Quantum Theory by David Bohm. But now we're going to be looking at, well, why did I start off episode 27 of our differential geometry reading streams here with Bohmian quantum mechanics, okay? The United States Department of Defense and the intelligence community are withholding information about anomalous phenomena from Congress. Hal Puthoff tells Nick Cook that the evidence is pretty solid that there are black budget aerospace programs that contravene white world understanding of the laws of physics. Two scientists connected with the DIA and NSA claim in a face-to-face meeting that the U.S. government or U.S. government contractors are engaged in programs that attempt to control NHI and harness those NHI for military and intelligence purposes. The scientists claim the research of David Bohm has been expanded upon. Anyways, so it's just reassuring that once you get through everything in Wald's general relativity and once you read Ed Witten's light rays, singularities and all that, that there is still more to go in understanding physics. You know what I'm saying? So it's like, let's keep the intellectual quest going, dog. You know what I'm saying? It's all good, man. Salut tout le monde. Welcome back to another differential geometry reading stream. I'm Anthony, obviously, and in these videos I've been reading Differential Geometry by Erwin Kreisig, Dover edition, out loud for you guys. And I also display the text on screen. And I also, in the beginning of all of these, I have these little intros where I talk about something maybe related to, hopefully, what I read in that section in that episode, but often we find that it is not directly related to it. But I like to keep it all within the realms of differential geometry, general relativity, physics, because differential geometry, as we've seen, is pretty much like the language of general relativity, and this book really emphasizes topics to that end. But like I said, we're going to start off with something a little bit different, and I'm going to be reading from Quantum Theory by David Bohm, which we'll see why I'm reading from this book in a second here. And I'm not going to read entire sections at first here. I'm going to start in the very beginning of part 1 on physical formulation of the quantum theory. I guess maybe I will talk a little bit about why I'm reading this. First is that in a lot of these videos I've alluded to philosophical problems in physics that are kind of at the forefront of some of the debates in physics right now, you could say. These questions are often about the interpretations of quantum mechanics. In short, what is actually happening in quantum mechanics, or if we have meaningful calculations, then what's the physical interpretation of those? So, like I said, they're very philosophical about the nature of reality, you could say, at that level. But then there's also the questions about the metaphysics of space and time, which I kind of alluded to in some of the previous differential geometry reading stream episodes, like I said, that we've had here. So, but from what I've gathered, some physicists would say that the quantum mechanics questions come first. The questions about space and time come later. So when you're thinking about the interpretations of quantum mechanics, there are three main camps, you could say. The first camp is perhaps seen as a conservative, smaller yet outspoken group, which favors the notion that position, velocity or momentum, and the wave function all exist as corresponding to actual physical phenomena that are actually happening in reality. And this is the school of thought of David Bohm and is referred to as the hidden variables theory. So namely that within the framework of going from classical physics before to quantum mechanics, we've gained a greater understanding with Schrodinger's equation and all of that, but there are still as yet undiscovered or not yet understood variables that contribute to the framework of understanding all of that stuff that we just don't have yet, basically. The second camp is a little bit radical in that it denies any sort of reality that pre-exists our observations. And so basically position and velocity don't really exist. But what really is going on is just the wave function. And this is the school of thought of Niels Bohr, Heisenberg, guys like Max Born, and this is called then the Copenhagen interpretation. So a mantra that kind of sums it all up, I think for me, for the Copenhagen interpretation is don't think, just calculate. And then the third school of thought for interpretations of quantum mechanics is the so-called many worlds interpretation. And so anyways, with that, I'm going to keep reading now from part 1 of Quantum Theory by David Bohm, where he's talking about how did we get to this quantum theory that he's describing in his book. So he says, in the first part of this book, an unusual amount of attention is given to the steps by which the quantum theory may be developed, starting with classical theory and with specific experiments that led to the replacement of classical theory by the quantum theory. The experiments are presented not in historical order, but rather in what may be called a logical order, and I would add, maybe you could call it a dialectical order. An historical order would contain many confusing elements that would hide the inherent unity that the quantum theory possesses. In this book, the experimental and theoretical developments are presented in such a way as to emphasize this unity and to show that each new step is either based directly on experiment or else follows logically from the previous steps. In this manner, the quantum theory can be made to seem less like a strange and somewhat arbitrary prescription justified only by the fact that the results of its abstruse mathematical calculations happen to agree with experiment. So I don't think we could have, with that last sentence, a more clear philosophical opposition to the Copenhagen interpretations, don't think, just calculate. And we're reading, of course, may I remind you, from David Bohm's book. So now I'm going to skip ahead here a little bit, and I'm going to read a quick chapter here. It's only 3 pages long. And it's basically just the overview of what Bohm described, where you go from classical physics and experiment by experiment, or building up from the logical conclusions from the math, getting to the, I guess you could say, next step in the development of quantum theory. So chapter 7 is a 3-page summary of all of that, so let's read it here. Starting with Planck's hypothesis that the radiation oscillators are restricted to discrete energy states with capital E equals nh times v, we have come a long way. Although this hypothesis is totally at variance with all of classical physics, it gives a quantitative prediction of the electromagnetic spectrum emitted by a black body, which is in perfect agreement with experiments at all temperatures and frequencies that have ever been measured. Simply because radiation oscillators are in thermodynamic equilibrium with material oscillators in the walls, we are led now to expect that the material oscillators have their energies quantized in the same way. Einstein and Debye obtained a quantitative fit with the specific heats of a wide range of solids when they applied this idea to the vibrations of the atoms composing the solid. The next step was to apply the idea of quantization of the energy of the radiation oscillators to exchanges of energy between electromagnetic fields and charged particles, such as electrons. This idea requires that these exchanges occur in quanta with capital E equals hv. This is exactly what is observed in the photoelectric effect. On the other hand, classical theory, which predicts a gradual transfer of energy, is clearly shown to be wrong. The fact that the energy of the oscillators is restricted to multiples of a definite unit suggests that the process of transferring energy to an electron is indivisible, since if it were not, there would be an intermediate state in which the oscillator had part of a quantum. Many experiments in connection with the photoelectric effect, Compton effect, and other problems have verified the indivisibility of all quantum processes. Because the energy of a radiation oscillator can be transferred to an electron only in quanta, the electromagnetic wave takes on many particle-like properties. In particular, the sudden appearance of all the energy at one point suggests that light is made up of particles. Yet, even when only a single photon is present, light demonstrates certain interference properties which suggest equally strongly that it is a wave. Here we meet for the first time the wave-particle duality, characteristic of all material systems in quantum theory. Under some circumstances, light shows interference properties and acts very much like a wave, while in other circumstances it acts like a particle. The two aspects are related by the fact that the wave intensity determines the probability that all the energy appears at one point as if the system were a particle. Thus, we see how probability, the wave-particle duality, and the indivisibility of quantum transfers are all related. We then asked how it came about that, on a macroscopic scale, the continuous deterministic laws of classical physics seemed to be true, whereas on a fundamental level the basic processes were discontinuous and had only their probabilities determined. The answer lies in the correspondence principle, which is based on the idea that, first, the discontinuities are too small to be seen on a classical level, and second, that so many quantum processes take place in any classical process that the deviation of the actual result from the statistical average is negligible. In order that quantum laws lead to correct classical laws, it is necessary to limit severely both the possible spacings of the quantum states and the probabilities of quantum processes. For example, with the aid of the correspondence principle, we derived the Bohr-Sommerfeld conditions for the quantization of action. These conditions then led to a large number of predictions that are in accord with experiment. In a similar way, the probability of radiation could be predicted roughly from the requirement that it must yield the correct classical rate of radiation in the correspondence limit. The theory still suffered from three defects, however. First, it applied only to periodic motions. Second, it gave no account of what happens in the transition from one energy level to another. And finally, it was unable to deal with complex atoms. All these defects were eventually removed by the wave theory of de Broglie and Schrödinger. The quantization of action follows naturally from boundary conditions on the waves in periodic systems. Yet, aperiodic systems are described by wave packets that move with an average velocity equal to that of the classical particles in their trajectories. The transitions between orbits are described as the gradual flow of the wave from one orbit to the next. Later, we shall see that with Schrödinger's equations, we can treat all systems, however complex, and get quantitatively correct results in a tremendous number of applications, covering a range of fields from spectroscopy, chemistry, and the theory of solids, to electrical conductivity, X-rays, and the theory of atomic structure. In all these fields, classical physics fails, and quantum physics gives the right results. Although the wave theory is successful, it raises some paradoxes of its own. The wave theory successfully explains interference effects, such as those observed in the Davison-Germer experiment. Yet, even after an electron or an electromagnetic wave has clearly suffered diffraction, it is always possible to find the electron or photon at some definite position. In a similar way, although the wave flows gradually from one orbit to the next, the process of energy transfer is still indivisible, because experiment shows that the atom either absorbs the full energy of a quantum or absorbs none. If we recall that the quantum laws are known to be laws of probability only, the most natural interpretation of these results is that the wave yields the probability of finding a particle in a given region. In a similar way, we can show that the intensity of a given Fourier component, the magnitude squared of lowercase phi of k, yields only the probability that the momentum has the value p equals h bar k. This means that matter can exhibit under different conditions either wave-like or particle-like behavior, that is to say, it shows a wave-particle duality in its properties. The linkage between wave intensity and probability on the one hand, combined with the linkage between wavelength and momentum on the other hand, leads to the uncertainty principle, which is one of the most important results of the wave-particle duality. This uncertainty principle provides a more precise limitation on the applicability of the concepts of classical determinism than we were able to get without the aid of the wave picture. Finally, we saw that in any actual measurement process, there was always one stage where the uncontrollable and unpredictable transfer of an indivisible quantum intervened to prevent us from drawing inferences about the system under observation that were more accurate than the limitations given by the uncertainty principle. Because the uncertainty principle, which is predicted from the wave-particle duality, requires for its verification the elements of indivisibility of quantum transfers and incomplete predictability of when and where the transfer takes place, we conclude that all three elements must be included to obtain a consistent quantum theory. Thus, the quantum theory possesses a very complete internal unity, such that each part works together with the others in an interlocking way, and such that the whole theory would fail unless each part were present. Finally, we saw that even the wave function undergoes indivisible and uncontrollable changes when the object under observation interacts with a measuring apparatus. This behavior of the wave function leads to qualitative description of the properties of matter in terms of incompletely defined and mutually incompatible potentialities, which can be realized more fully only in interaction with a suitable system in the environment. For example, whether an electron shows more wave-like or more particle-like properties depends on whether it interacts with something that tends to bring out its wave-like or particle-like aspects. We are thus led to regard matter as something more fluid and dependent on the environment than classical physics would lead us to suppose. The further consequences of this new concept of matter will be discussed in chapters 8 and 22 within Quantum Theory by David Bohm, but now we're going to be looking at, well, why did I start off episode 27 of our differential geometry reading streams here with Bohmian quantum mechanics, okay? I don't know if you guys in America or maybe even internationally have been following the U.S. congressional hearings, but last year there was testimony to Congress on the Tic Tac incident, you could call it, which is from the early 2000s by, I believe, Dave Fravor, and then there's the separate stuff about, you know, just like the classified compartmentalization of UAP programs from David Grush, but that was all reported on in the New York Times in 2017 after it kind of like happened in the early 2000s. And then last year, so 2023, Dave Fravor, David Grush, and then Ryan Graves was another like Air Force or Navy pilot who also observed these Tic Tacs and stuff. But anyways, those three are considered whistleblowers, testified last year. And then a few days ago, as of recording this, on November 13, yeah, I guess this document has the wrong year on it because the hearing was this year, 2024, and it says on the first page here, November 13, 2023. But anyways, South Carolina House Representative Nancy Mace held this hearing, and there was Lou Elizondo, and then this other guy, Michael Schellenberger, and then one other guy, I forgot who the third guy was, but this Michael Schellenberger submitted this written testimony, which, as you can see, is titled "The United States Department of Defense and the Intelligence Community are withholding information about anomalous phenomena from Congress." And there's like whatever, a dozen pages where he kind of gives like a summary of what it's all about. But then the bulk of this is like a 200-page timeline of supposedly like the UAP stuff that's been covered up by the US government, going back to basically Roswell, so 1947. And I think that if this is not actually real stuff, then this guy, Michael Schellenberger, missed a huge opportunity to take this timeline and just like turn it into a fiction novel, because the substance of this, if you're like a really good writer, like, I don't know, say Thomas Pynchon, then you could write a book that really slaps, like Gravity's Rainbow. You know what I'm saying? Like, okay, The Three Body Problem by Liu Cixin, great book, great series. I mean, I see people out in public reading the books from that series. I read the first one. It's a, you know, great science fiction. The stuff in this timeline slaps. So if it's not like real, live, legit stuff, then if it's like a hoax or whatever, he might as well have just wrote a science fiction novel that slaps. Anyways, I don't really care about some of that stuff, to be honest with you. I'm just caring about the physics. So we're just going to start in 1991. We got here November 25, 1991, two scientists connected with the DIA and NSA claim in a face-to-face meeting that the U.S. government or U.S. government contractors are engaged in programs that attempt to control NHI and harness those NHI for military and intelligence purposes. Good for them! What's really interesting to me is the next paragraph where they say the scientists claim the research of David Bohm has been expanded upon, that everything exists everywhere at once and folded into an invisible, timeless medium. So that's pretty cool. We're now going to go on and read a part from 1998. We got here January of 1998. James Cox of Anti-Gravity News and Space Drive Technology proposes 7 types of anti-gravity devices can theoretically exist. Also, before I read those 7, elsewhere in this huge 200-page timeline, there's mention of Ed Witten's dad. There's mention of also, though, like Tom DeLonge. There's also mention of, you know, Hal Puthoff. Like I said, Roswell, like so much stuff. But anyways, we've got 7 types of anti-gravity devices can theoretically exist, according to this guy, James Cox, in January of 1998. Were some of you watching Even Alive in 1998? Comment down below. 1, we have mechanical, using high-speed rotation based on the work of all these guys who I don't know. Some of you might. Number 2, acoustical with no moving parts and employ vibration to alter nuclear interactions with gravity based on the work of some guys that I don't know. But then interestingly, Tibetan stone levitation. I think that's cool. 3, rotating disc or cone. Reminder to buy a Figure 69 cone Anthony Makes Videos t-shirt. Coming to you soon. Rotating disc or cone using stationary electrodes at high voltage based on the work of TT, don't know. Then we've got Brown Bielfeld, probably mispronouncing that, but Brown Bielfeld, those are big names in physics. But then these other guys I don't know about. 4, AC or RF or microwave E&M devices based on the work of some guys who I don't know, but then Nikola Tesla, okay, shout out to that guy. Number 5, solid state devices using anti-gravitic or shielding based on the work of Podolketnov perhaps, and Schnurrer, but that sounds like it's going to be using like ceramic piezoelectrics or, you know, like some crazy plasma metamaterials, you know what I'm saying? Number 6, nuclear anti-gravitation that allegedly causes a breakdown of Newton's third law based on the alleged work of some people who we don't know. But then we also have, right, like all kinds of name drops in this document. The claims of Robert Lazar, element 115, unipentium, and some other guy who I don't know. It is alleged that cold fusion with zero-point energy interaction can achieve this effect. Very interesting. Also, comment down below if you know what Newton's third law of motion is even, okay? Just comment that down below. Number 7, we have biological anti-gravity devices involving the human or animal element to achieve weightlessness based on the alleged claims of, I don't know, all this stuff. But then Russian mirror chamber research. I don't know what that is, but it sounds like it could be a cool Wikipedia article. Moving right along, just a few more of these that I'm going to shout out. We're going to go from 1998 to 2001 here in our little YouTube time hop here. Oh, we're in 2000. That's why I was like, where is it here? Okay. June 2001. James Woodward. I wonder if he's related to Bob Woodward. Probably not. And Thomas Mahood of Cal State University and Paul March of Lockheed Martin Space Operations published a paper on altering the mass of small test samples of lead zirconate titanate, PZT, a piezoelectric compound. Woodward and March achieved small mass reduction with small energies and say large mass fluctuation of PZT could be achieved with only moderately increased power, but it's beyond the scope of that study. Check out that study. And we're going to get to the last one that we're going to read here before going into Differential Geometry by Erwin Kreisig. We have at some point in the year 2002, this author, Nick Cook, whoever he is, states Hal Puthoff, who is the eventual ATIP scientist. I'm sure we can all find podcasts of Hal Puthoff being cryptic and not forthcoming all over YouTube right now. Hal Puthoff tells Nick Cook that the evidence is pretty solid that there are black budget aerospace programs that contravene white world understanding of the laws of physics. Puthoff states the most likely candidate for exotic propulsion is the perturbation of space-time by understanding the link between electromagnetism and gravity. And then we have an associated note, which is kind of along the lines of the previous one that I read from January of 1998, where there were the 7 theoretical types of anti-gravity devices. We have in the note here NASA BPP, where BPP, that stands for the Breakthrough Propulsion Physics Program. So probably BPPP, but it's just BPP. A little trigraph for you. Anyways, NASA BPPP was working on 5 methods of anti-gravity at this time. 1. Inertia change through sudden energy density change. 2. Zero-point energy. 3. Perturbation of space-time through electromagnetism and gravity. 4. Superluminal quantum tunneling. 5. Gravity shielding through the use of rapidly spinning superconductors. And Hal Puthoff claimed that number 3, the interaction of electromagnetism and gravity with that 0 point she, was the most likely to be fueling the development of a black budget anti-gravity program at the time. Anyways, so it's just reassuring that once you get through everything in Wald's general relativity, and once you read Ed Witten's light rays, singularities, and all that, that there is still more to go in understanding physics. You know what I'm saying? So it's like, let's keep the intellectual quest going, dog. You know what I'm saying? It's all good, man. Anywho, back to the differential geometry. We're reading from chapter 6, formerly called mappings, but the chapter might as well just be called conformal mappings. Anyways, we are in section 65, conformal mapping of a sphere into a plane, stereographic and Mercator projection. Like I said, I'm still editing Differential Geometry Reading Stream episode 26. We're in 27 right now. You might as well just read the Wikipedia articles on stereographic projection and Mercator projection while you're at it, because otherwise I was going to at the beginning of this video, but clearly already we're probably like 30 minutes in. We need to get back to reading the book, okay? Mappings of a sphere into a plane are of basic interest, especially because of their application to the practical problem of constructing maps of the globe. Problems of that type were considered by Lambert in 1772, Euler, Lagrange, Gauss, and others. It is known that the globe may be considered as a sphere of radius 6,371 kilometers. Since the Gaussian curvature of the plane is 0, while a sphere of radius r has the Gaussian curvature capital K equals 1 over r squared, it is clear that no portion of the sphere can be mapped isometrically into a plane, for which refer back to in section 57, theorem 57.2. which states that isometric surfaces have the same Gaussian curvature at corresponding points. Corresponding curves on those surfaces have the same geodesic curvature at corresponding points. Hence, there cannot exist a map of a portion of the globe which is exactly isometric. This fact can be proved in an elementary manner without using Theorem 57.2, for which referred to Self-Plug by Erwin Kreisig to his own work, but we can find conformal and equiareal mappings of a sphere into a plane. Some of them possess additional properties which are important for practical reasons. Clearly, the choice of the mapping depends on the purpose of the map to be constructed, and also on the location and size of the portion of the globe to be mapped. We mentioned that the globe can be approximated more exactly by an ellipsoid of revolution with radius 6,378 kilometers at the equator, and with a distance of the poles from the center of 6,357 kilometers. A first important example of a conformal mapping of a sphere into a plane is the stereographic projection. This mapping was most likely discovered by Hipparch, circa 160 BC. The name stereographic projection was introduced by d'Aiguillon in 1613. The stereographic projection is obtained by projecting the points of the sphere from a point capital S on the sphere called the center of projection on the tangent plane to the sphere at the point diametrically opposite to S. By this projection, the whole sphere, with the exception of the point S, is mapped one-to-one onto the open plane. In figure 76 on the next page, which I'll hopefully have on the screen right now, the south pole of the globe has been chosen as the center of projection. The images of the circles parallel to the equator are concentric circles with center at the north pole, n star equals n. The images of the meridians are straight lines through n star. The inverse image of an arbitrary straight line capital G star is a circle on the sphere passing through S, since the projecting straight lines corresponding to G star lie in a plane which intersects the sphere along a circle. Stereographic projection is conformal. We may prove this as follows. Let C1 and C2 be any two curves on the sphere capital F intersecting at a point capital P. Let capital T1 and capital T2 respectively be the tangents to C1 and C2 at P. We denote by C1 star, C2 star, and P star respectively the images of C1, C2, and P, and by capital S star sub alpha the tangents to capital C star sub alpha, where alpha is either 1 or 2, at P star. The inverse images S1 and S2 of those tangents are circles which intersect at P and S, the angle of intersection being the same at both points. The tangents to S1 and S2 at S are parallel to S1 star and S2 star respectively. The angle of intersection of these tangents at S is therefore equal to that of S1 star and S2 star. Hence, the same holds for the tangents to S1 and S2 at P, which coincides with the tangents T1 and T2 to C1 and C2 at P. This completes the proof. Stereographic projection has the following interesting property. It maps every circle on the sphere F onto a circle or a straight line in the plane. This fact can be proved as follows. We choose Cartesian coordinates x1, x2, and x3 in space such that the point N of F becomes the origin, and the positive rays of the x1 and x2 axis coincide with those of the Cartesian x1 star and x2 star coordinate system in the image plane. For the sake of simplicity, we choose the diameter of the sphere F to be 1. Then S coincides with the unit point on the x3 axis. If P, not equal to S, is an arbitrary point of F, and P star its image, then, referring back to figure 75 on the previous page depicting stereographic projection, R star squared equals x1 star squared plus x2 star squared, h equals x3. The ratio of x3 to r is equal to the ratio of r star to 1, and the ratio of r to the quantity 1 minus x3 is equal to the ratio of r star to 1. Hence, r equals a fraction with the numerator r star over a denominator of 1 plus r star squared, and x3 is equal to a fraction with the numerator of r star squared and a denominator of 1 plus r star squared. Setting x1 star to r star times cosine alpha and x1 to r cosine alpha. Furthermore, setting x2 star equal to r star sine alpha and x2 to r sine alpha, we have that x1 is equal to x1 star over a, x2 is equal to x2 star over a, and x3 is equal to the quantity x1 star squared plus x2 star squared all over the denominator a, where a is equal to 1 plus x1 star squared plus x2 star squared, and conversely, x1 star equals x1 over c, x2 star equals x2 over c, and r star squared is equal to x3 over c, where c is equal to 1 minus x3. By inserting these expressions into the equation of a circle in the image plane, capital A times the quantity x1 star squared plus x2 star squared closed quantity plus capital B times x1 star plus capital C times x2 star plus capital D all equals 0, we see that the corresponding inverse image is represented by the linear equation capital A times x3 plus capital B times x1 plus capital C times x2 plus capital D times the quantity 1 minus x3 closed quantity all equal to 0. Hence, this inverse image is a plane curve on the sphere, that is, a circle. We mentioned without giving the proof that the stereographic projection is the only conformal mapping of a sphere onto a plane which maps circles onto circles. This result was first obtained by Lagrange. The Mercator projection is another important conformal mapping of the sphere onto the plane. This mapping was introduced in 1569 by Gerardus Mercator, where Mercator is Latinized for Kramer, and he lived from 1512 to 1594. And when Gerardus Mercator introduced this, he did not indicate a mathematical procedure of construction. This was not communicated until much later by Haley in 1695. So using the representation from the earlier section 25 of the sphere, we have ds squared is equal to r squared times the quantity cosine squared of u squared then times du1 squared plus du2 squared closed quantity is equal to r squared times the cosine squared of u2 then times the quantity du1 squared plus the secant squared of u2 then times du2 squared closed quantity. Therefore, we set dx1 star equal to du1 and set dx2 star equal to the secant of u2 then times du2, where the magnitude of u2 is less than pi over 2. Or we set x1 star equal to u1 and x2 star equal to the log of the tangent of the quantity u2 over 2 then plus pi over 4 closed quantity, where again the magnitude of u2 is less than but not equal to pi over 2. And after setting this, we introduce x1 star and x2 star as Cartesian coordinates in the image plane capital F star. Then the Mercator projection of the sphere, represented by what was given in section 25, onto the plane F star is accomplished by what we had just set for x1 star and x2 star. Since the coefficients of the first fundamental form of the sphere and of the plane are proportional, the mapping is conformal. The images of the meridians u1 equal to c1 equal to a constant are the straight lines where x1 star equal to c1 is equal to a constant. The circles where u2 equal to c2 equal to a constant, parallel to the equator where u2 equals 0, are mapped onto straight lines, namely x2 star is equal to the logarithm of the tangent of the quantity c2 over 2 then plus pi over 4 closed quantity. The mapping is satisfactory near the equator but gives an exaggerated impression of the dimensions of Arctic regions, for which refer to figure 77 below. Curves of constant direction, for instance, continually northeast on the globe, are called loxodromes. We saw loxodromic Mobius transformations on the Riemann sphere in like 3 episodes ago to this one, in like the first episode where I started talking about conformal mappings. We looked at like elliptic, parabolic, hyperbolic, and loxodromic Mobius transformations on the Riemann sphere. Interesting stuff. Anyways, special cases of these curves are the meridians and parallels. The general type of a loxodrome is a curve which winds around the poles an infinity of times and approaches them more and more, which is recapitulated in the images we saw, which I'll probably just throw up on the screen right now, of those Mobius transformations onto a Riemann sphere. What the heck, you know what I mean? Anyways, the images of loxodromes are straight lines. This fact can be proved as follows. By definition, any loxodrome intersects every meridian at the same angle. Since the Mercator projection is conformal, the image of the loxodrome intersects the images of the meridians also at a constant angle. Now those images are parallel straight lines. This completes the proof. And yeah, so I'm pretty sure, like I mentioned also a few episodes ago, starting now in section 65 through section 67, these are sections that are cited in the Kuno book for what it's worth in differential geometry. So if you want to know about mappings in differential geometry, this apparently is where it's at. We started off reading from some Bohmian quantum mechanics. We read parts of some US congressional testimony on unidentified anomalous phenomena as of this month, November, this year of our Lord, 2024. And we read a section from Differential Geometry by our boy, may he rest in peace, Erwin Kreisig. I hope you guys aren't mad that I'm not reading like more sections, closer to 3 or 4 sections in each one of these videos, but trying to put a little more personality, a little more flavor, not be as mechanical, just reading and then, you know, editing it to be as condensed as possible, trying to add my own takes, thoughts. I'm going to do more freestyles hopefully in the future, some more meow sections, math in your own words. Speaking of cats, my cat's sleeping right now, otherwise I'd show him right now. Peep the outfit. We've got the gray pinstripe suit today. White, I guess maybe you'd call this a broad collar. It's not the button down, right? You can see that. French cuffs, white shirt, yellow foulard tie, black socks, black belt, no watch, but got the married to myself ring, and I would rock this outfit maybe with the black penny loafers, most likely though with the black cap-toe Oxfords, the lace-ups, because, you know, those CIA guys, you can always tell because they're wearing lace-up shoes. If you want to run and get somewhere faster or run getting away from something faster, go with those lace-ups. Avoid those slip-ons. But if you're going to the airport, you might want to wear slip-ons. Anyways, see you guys in the next one. Peace.